Hello everyone. In this video we will be discussing about singular value decomposition. So in the previous video we have discussed about diagonalization or eigen decomposition of a matrix which is restricted to square matrices. So if we have a square matrix A, so eigen decomposition looks like x lambda x inverse, and if it is a symmetric matrix then we have A is equal to x lambda x transpose, where x is the eigenvector in matrix which contains independent eigenvectors. So but singular value decomposition is more generic, which is also applicable for a rectangular matrix. So consider a matrix A which is of dimension m cross n. So A can be decomposed as U sigma V transpose. Here the dimensions are very important, or where A has m cross n and U is m cross m, which means a square matrix, and sigma is a m cross n, which is a rectangular matrix, and V is a square matrix of dimension n cross n. So as you can see here, sigma and A has same size, same order. So let us also see how U and V are computed. So U is nothing but the eigenvectors of A transpose, and V is the eigenvectors of A transpose A. So sigma is a rectangular diagonal matrix with diagonal values which are non-zero, and these diagonal values are computed by obtaining the eigenvalues of A transpose A or A transpose. Suppose if the rank of the matrix A is R, then there are R eigenvalues of A transpose A or A transpose which are equal, and we take the square root of those eigenvalues to obtain the singular values in sigma. So sigma contains non-zero square roots of the eigenvalues of A transpose A or A transpose. So it's important to see how these matrices look like for fat matrix and a tall matrix. So consider first a fat matrix A. So it looks something like this. U would be a small matrix of dimension m cross m, and sigma would be a dimension m cross n, and V would be of dimension n cross n. So if the matrix A is full rank, which means that if it is of rank m, then m diagonal elements, first m diagonal elements positions will be occupied by the singular values, and the rest of the values are all zeros. For tall matrix, when m is greater than n, it looks something like this. So U is a bigger matrix of dimension m cross m, sigma is of m cross n, and V is of n cross n. So when the rank of the matrix is n, then we have U has m cross m, and when rank of the matrix is full rank, that means there are n eigenvalue, n independent vectors, then we have n singular values which occupy the diagonal positions, and the rest of the values are 0 in sigma. So this is how it looks for both fat matrix and tall matrix. So let us see more details about sigma and where this SVD is being used. So when m is less than n, so the matrix sigma looks something like this. So that it occupies the m diagonal elements, and the rest of the values are all zeros. And there are a number of columns which occupies only 0 vectors, because n is greater than m, and if m is greater than n, sigma looks something like this. So the first n diagonal values would be occupied with singular values, and the rest of the values are all zeros. So let us see how singular values and what is the significance of singular values and how it behaves for various different types of matrices. For positive definite matrices, which means that when A has eigenvalues greater than 0, sigma would be equal to lambda, and U sigma V transpose is similar to eigenvalue decomposition, which is x lambda x transpose. So for other symmetric matrices, any negative eigenvalues in lambda becomes positive in sigma. So we have already seen that symmetric matrix can be represented as A is equal to X lambda X transpose, and any negative eigenvalues in sigma, because symmetric matrix does not impose any condition on the eigenvalues. So if there are any negative eigenvalues in sigma, they become positive in if there is any negative value in lambda, they become positive in sigma. So if A is equal to U sigma V transpose, the pseudo inverse A plus can be computed as V sigma plus U transpose. Here sigma plus is since sigma is a diagonal rectangular diagonal matrix, so sigma plus contains the inverse of the singular values, so that would be shown in a while. So given a general matrix, it can be m greater than n or m less than n or m is equal to n. Solutions to system of equation Ax equal to b can be computed using singular value decomposition, and it is called as minimum length least square solution. So that solution can be computed by V sigma plus U transpose B. So we are using the pseudo inverse and multiplying with the B to obtain the solution X plus. First of all, what is sigma plus? Let us understand that. So sigma plus is computed for m greater than n and m less than n as follows. So for m greater than n, dimension of the sigma was m cross n, whereas sigma plus has dimension n cross m. So and the values of diagonal positions are inverse of the values which are there in the original sigma matrix. For m less than n, the dimension of sigma would be m cross n, whereas sigma plus would be n cross m, and it occupies the m diagonal positions with inverted singular values. So this is how singular values are computed, and this is how it is being used in the computation of for solutions to the system of equations and also inverse of a matrix. So let us see now some examples of how it looks like. So consider a fat matrix A. So its dimensions can be represented as follows. It's a 2 cross 3 matrix, and U dimension is of 2 cross 2 and sigma is of 2 cross 3 and V is of 3 cross 3. So U, when you compute the eigenvectors of A transpose, you will be having something like this, and V is also computed are the eigenvectors. So sigma contains the singular values, and the singular values, as we have seen earlier, are the square roots of the eigenvalues of A transpose or A transpose A. In fact, A transpose and A transpose A will have the similar eigenvalues, and we will be taking the square root of those eigenvalues, and sigma occupies the diagonal positions of the sigma occupies those singular values. And for tall matrix, it looks something like this. U would be of bigger matrix 3 cross 3 and V would be 2 cross 2, and sigma will contain singular values in its diagonal positions, but since here A is a dependent matrix, we have only one eigenvalue, positive eigenvalue, the other eigenvalue is 0. So this is examples of SVD. This is how it looks like, but let us see a practical application of where singular value decomposition is applied. So I am taking a image which is Ingenuity image, which is taken on Mars, and this image is a RGB image and it is converted to a grayscale image, and we are attempting to see if we could compress this image using SVD. So the primary motivation of this particular example is in a satellite applications or a space applications, there is a lot of data and it is kind of harder to send the data from the satellite. So is it possible for us to kind of compress by taking a limited number of singular values? So the idea is rather than taking all the singular values, take the first few largest singular values and construct the matrix out of it. And it is found that if you construct that using the first few singular values, it is almost possible to construct the matrix, and this is shown mathematically here, where A is UR, sigma R, and VR transpose. So here U matrix is not anymore square matrix. U is of dimension M cross R, and sigma R is of dimension R cross R, and VR is of dimension R cross N. So such a matrix will have the first R singular values, is constructed based on R singular values. We can illustrate this with this example by reconstructing the images for various singular values. So as we can see here, for 4 singular values, this is how it looks like. For 8, it would look like this. For 16 singular values, we are able to construct the image. As you can see, for 32, it's almost like we are able to see the image properly. For 64, it improves further, but the changes are less visible. So there is, as we move on, increase the values of number of singular values, there is no much change. That means the most of the image details are captured by the first few singular values. So this is the importance of singular value decomposition. So it can capture the important features in the first few singular values, and a lot of dimensionality reduction can be done. So if we are able to send the first few singular value eigenvectors and its singular values, that would be sufficient to construct the almost closer picture of the original image. So we have such a fantastic applications of singular value decomposition. There are other applications also, and we are confining it to this one particular application in this video. Yeah, so yeah, that's it. So thank you.